Greetings to everyone. Today we are going to discuss about understanding E1 and E2 reaction mechanisms in organic chemistry. What are E1 and E2 reactions? E1 is nothing but unimolecular elimination and E2 is nothing but bimolecular elimination. First we are going to discuss about unimolecular elimination. It has two steps and it proceeds via carbocation intermediate. The substrate loses its leaving group first and then it will form a positively charged carbon center, then eliminates a proton to generate alkene product. In E2, it is a one-step process because this mechanism proceeds via transition state, where base-induced proton removal and leaving group departure occur simultaneously. So, no intermediate forms during this synchronized transformation. Both mechanisms converted saturated compounds into alkenes, that is unsaturated compounds, removing a proton and the leaving group in the adjacent carbons, but their pathways different fundamentally. Key difference in mechanism and kinetics. K1 kinetics. Rate depends only on the concentration of substrate. So it is called as first order kinetics. So we can denote rate is equal to K into concentration of substrate. In E2 kinetics, rate depends on both concentration of substrate as well as the concentration of the base. So rate is equal to proportionality constant K into concentration of substrate and concentration of base. And these are the evidences which can support E1 mechanism. Number 1, first order kinetics. E1 is the first order kinetics. Experimental rate measurements shows depends only on the substrate concentration consistent with the carbocation formation as the rate limiting step or rate determining step. Changing base concentration has no effect on the rate. The second evidence is absence of isotope effect. If hydrogen is replaced by its isotope like deuterium, the CH bond breaking occurs after the slow or rate determining step. So this confirms that stepwise nature of the mechanism. And third evidence is carbocation rearrangement. If a less stable carbocation is formed in the intermediate, it can rearrange itself to form more stable carbocation. That is called as carbocation intermediate. And then the fourth one is relaxed stereochemistry. The planar carbocation intermediate allows proton removal from any adjacent carbon without strict geometrical requirements, leading to the mixture of stereoisomers. And these are the evidences supporting E2 mechanism. It is a second order kinetics which comes from the rate of the reaction depends on concentration of substrate as well as the concentration of the base. And a strong isotope effect. Replacing beta hydrogen with deuterium causes a significant rate reduction, that is Kh by Kd is equal to 3 to 8 units, proving that CH bond breakage or cleavage occurs during the rate limiting transition state. And anti-periplanar requirement, the beta hydrogen and the leaving group must adopt anti-periplanar geometry. That is, it should be present on the opposite direction with 180-degree dihedral angle. For proper orbital overlap, the strict stereochemical constraint leads to the highly predictable product stereochemistry. Then absence of rearrangement. No carbocation formation occur here and this reaction proceeds via transition state. So here we have no rearrangement. Then stereospecific elimination occurs in E2. Stereochemical flexibility can occur in E1 reaction. In E2, the anti-periplanar requirement creates strict geometry constraints. The beta hydrogen and the leaving group must postulated 180-degree apart from optimal orbital overlap in the transition state. This geometry necessity leads to stereospecific elimination, typically favoring formation of the more stable transalkene, that is the base abstract only the hydrogen in the correct spatial orientation. But in the stereochemical flexibility of E1, the planar carbocation intermediate has only sp2 hybridization with the empty p orbital in the perpendicular to the molecular plate. So this geometry permits proton removal from any adjacent carbon without geometrical constraints. Consequently, even reactions produce mixture of cis and trans alkene with ratio determined by the thermodynamic stability rather than stereochemical requirement. Experimental insights in deuterium isotopes: 7x the E2 rate difference, 3 to 8x typically KIE range, and approximately 1 E1 rate ratio. What is the difference? Why this differences occur means in E2 reaction, CH bond breaking occurs during the rate determining step. The heavier deuterium atom requires more energy to remove, significantly slowing the reaction rate. But in the E1 mechanism, CH bond cleavage happens after carbocation formation in the fast and non-rate determining step. So isotope substituent therefore has no minimal impact on the overall rate of the reaction. So carbocation rearrangement, a signature of E1 reaction, not in the E2 reaction. So initial carbocation, second one is rearrangement, and third one is elimination can occur. Summary: when to expect E1 versus E2, E1 conditions, tertiary substrates can occur, can undergo the E1 mechanism very easily. And second one is weak bases enough polar protic solvent required to create carbocation, elevated temperature. In E2 condition, strong bulky bases should be required. Primary or secondary substrates can be taken anti-periplanar beta hydrogen accessible higher basic concentrations. Thank you.
அடுத்த